Welcome to qnawire.
In this problem, I want us to go back and look at problem 55 and look at the exergy destruction associated with reheating and regeneration processes. All right. So actually, let's go back and look at problem 55 if I zoom back here. Okay. So again, we have a reheat process here and a reheat process here and a regeneration process here. So again, we have, we're going to basically be looking at the exergy kind of around associated with these things here. So we have, let's see here, where are we now? 54. Yep. So we have Y, the percentage of flow coming out of the basically going back to be reheated out of the turbine. We calculated that. We can get the entropy at the reheat cycle. Let's see here. Let's actually do something in 55 that said. Let's actually copy some of these things. Let's copy this guy and draw a nice little boundary around here and not move it. I want to copy it, and that's 50, 65, 54. Let's paste that into here, that nice little guy there, so we can reference it. And let's go and copy our TS diagram too. So let's copy this guy. All right, draw a nice little boundary, and we'll keep our entropy. Isentropic entropy notes there, so copy that, and let's paste him into here. And that works out rather nicely. All right, so now we can reference these guys. So let's see here, a reheat right here. So again, out of the S1 and 2, okay, so that's again at the pump, and it's an isentropic pump. So we have the entropy there that we can look up because it's entropy at the saturated liquid at 10 kilopascals. At 3, we have a saturated liquid at 800 kilopascals, so we can get the entropy there. At 5 and 6, we calculated that before, and again, it's isentropic turbine. And then at 7, we calculated that before also, and we don't need it at 8 in this problem. So the heat transfer in the reheat is the enthalpy at 7 minus the enthalpy at 6. So we can get that is 668.6 kilojoules per kilogram. Again, we have high temperature and low temperatures in this problem. Now, in the reheat, the entropy destruction from this reheating is T naught times the entropy change in the exergy destruction is times the entropy change across, at this reheated flow here, and then minus the Q reheat, this heat transfer that went into this part of the fluid, and then again that was assumed to be at 1800 Kelvin. So the exergy destroyed in this reheating process is 214.3 kilojoules per kilogram. And now in the regeneration process, we gotta look at this guy here. So let's see here. We're assuming that this is adiabatic, so there's no heat transfer part here. So we're not worried about that. That goes to 0. And so the entropy exiting is at 3. So then we have entropy entering at 6, but we don't have the full amount coming in from 6. Just have a fraction y of it.
What do you got?
And then we have a fraction y, or 1 minus y of the coming in from, let's see here, from the pump here. So then that's the entropy at 2. And I multiplied that through. So again, this is just 1 minus y of the rest of the fluid coming in here. So again, basically it's just the entropy out minus the entropy in, and times the surrounding temperature, and we wind up with an entropy destruction, an exergy destruction of 47.8 kilojoules per kilogram. So we destroyed a little exergy in doing these, but we increased the overall efficiency, probably. I don't think we actually analyzed this problem without these, but I think these were these are put there to basically increase the overall efficiency of the problem of the turbine. So of the not of the turbine, of the whole process. So again, we can you know, get a lot of this stuff off of here, and so again, we see we did destroy some exergy in doing this.